This is our final video about multiple linear regression, and really it's just a summary of the process as a whole. So we'll be looking at the final version of the model we discuss on the website, which is labelled Model 7. So we're just going to really just show you how to run the model with the variables we included in Model 7, and also how to check that these sort of key assumptions have been met. So if we go to Analyze, Regression and Linear, we'll get the now familiar text box here. We're going to need to put our outcome variable, which is key stage 3 standardized score, in the dependent box. And this is what we've called a sort of value added model, whereby we're also using previous exam scores at age 11 as part of the model as a key predictor variable. So we'll add key stage 2 stand in the independence box. In this model we're also going to be including gender, so we'll find that, and we're going to be using the dummy variables for both ethnicity and the social economic class. So if we rearrange this by file order, it just makes it a little bit easier in this case to find the variables we're after. So we want E1 through to E7, which are these are our 7 ethnicity dummy variables, as I'm sure you remember by now. And we'll need SC1 through to SC7, which are our social economic status or social class variables. We'll also include SC0, which is the basically it's the dummy variable for when cases we don't have the information for those cases. Right, so if we go to statistics, we can start getting some of the information that we want with regard to the assumptions, and sort of testing whether or not the model's up to scratch, I guess. So we're going to need to get the confidence intervals. That's always useful to have, and it's also useful to have case-wise diagnostics. And because we've got such a large data set, we're probably only really interested in outliers outside 4 standard deviations. So what we'll be looking for is cases whereby the residual is 4 standard deviations away from the mean residual. We'll also get descriptives about each of our variables and the collinearity diagnostics in order just to check that we haven't got any problems with multicollinearity. Just click continue to close this box. Get the plots. So we'll put standardized residual on the y-axis and the standardized predicted score, on the x-axis, as we've done in the past. We'll also get a histogram and a normal probability plot, and these are just to check some of the assumptions. We'll talk about this more when we get to the output. And finally, we'll just talk about the saved options. As we've mentioned in previous videos, this is when you actually want to create a new variable, so a new piece of information for each case, which will just help you with your analysis. So you can get the predicted values from the model, which we've done in the past, the residual for each case, which we've also done in the past. We can also get something called a Cook's distance, which we talk about more on the website. We won't actually do here because it's sort of a long-winded and boring process, so it's not really appropriate for a video. But the Cook's distance is a good way of looking for outliers, of looking for influential cases. But as I say, for this video, to keep things sort of smooth, we won't add any of those saved variables. So this is sort of our basic Model 7, and we'll click OK. So let's have a look at what SPSS has given us. The first table here is the descriptive statistics for all our predictor variables and for our outcome variable. I mean, there's not a lot to do here, but it is worth looking at the number of participants which were actually included in the analysis. And obviously it's good to sort of have a summary of each of your key variables in order to understand your analysis and your data a little bit better. The next table is this monstrous correlations matrix. Again, I probably wouldn't sort of check through the whole thing unless you're concerned about signs of multicollinearity, which is basically when you've got 2 variables which are so highly correlated, so strongly related to one another, that you're concerned that the 2 variables are measuring the same thing. Having a quick look through the table, you can see that there aren't actually many correlations which are high. I mean, there's certainly a lot that are statistically significant, but that doesn't mean that they're so highly correlated that multicollinearity may be a concern. The only one that perhaps would be worth a quick look is the correlation between age 14 and age 11 standard marks, which is 0.886. So that indicates a very strong positive correlation between those two variables. But of course, you'd expect those two variables to be highly related, because that's previous achievement, exam performance with current exam performance, and 0.886 is still not a particularly concerning figure. If it was above 0.95, you may be more concerned about multicollinearity, but in this instance, it doesn't appear to be anything to worry about. So moving swiftly away from this rather horrifically large table, we go down to the variables entered removed table, which basically just tells you all the predictor variables that you've added into your model. And more interesting in the model summary and the ANOVA. So we can see from the R-square in the model summary that our model accounts for 79.7% of the variance in age 14 exam scores. So that's nearly 4/5 of the total variance that we've observed between participants at age 14 can be explained by the predictor variables that we've put into the model. So that, that's a good proportion. That gives us a bit of confidence that our model is going to be good at predicting the outcome. The ANOVA is sort of a direct test of how confident we can be in that regard. So it basically tests the model we've produced against using the mean as a model. So if we use the mean to predict each individual case's age 14 exam scores, would that be a more accurate way of predicting this final score than using our model? If this test is statistically significant, it means that it wouldn't be, and as you can see, this is way lower than the 0.05 probability value that we usually take to mean statistical significance. So let's move on to look at the all-important coefficients table, and we won't go into a huge amount of detail here because we've already spoken about it in previous videos, but it is worth reiterating how you go about interpreting each of the different types of coefficient, really. So we're looking in this sort of unstandardized coefficient B column here, and basically each of these coefficients tells us how much of a change in our outcome variable, which is standardized age 14 mark, can be explained by a change in each of these predictor variables. So for age 11 standard marks, which is a continuous variable like our outcome variable, a 1 point increase in age 11 marks is equivalent, will cause a change in the prediction for age 14 marks by 0.842, an increase by 0.842. So what we're saying is as age 11 scores increase, our model predicts an increase in age 14 marks. So it's 1 mark for this equals an increase of 0.842 marks for the outcome variable. It gets a little bit more complicated when we're looking at these dummy variables, or indeed any kind of dichotomous variable. So with gender, if you remember, we coded males as 0 and females as 1. So in this case, what we're actually looking at, the coefficient is the change between being the difference in the points predicted between being in category 0 and category 1. Because males were category 0 and females were category 1, we're actually looking at as you go from 0 to 1, you're looking at an increase of 0.556, which means that the model predicts females to score 0.556 more age 14 standard marks than males, and that's when you're controlling for all the other variables. So that includes all of these other variables within the model. You're still seeing this difference between males and females. It's works actually almost entirely the same with these dummy variables. The only thing you have to recall with the dummy variables is that you need to remember what your reference category is, so what in each of these cases 0 actually represents. So if you remember, for the ethnicity variable 0, our baseline category 0 is white British. So each of these is a comparison between white British and the stated ethnic category. So we can see that Indian students, for example, are predicted to get 1.413 more standardized marks than white British students, and again that's controlling for all of the other predictor variables. For the social economic class variables, what was our reference category? Our reference category was long-term unemployed, so that was 0. So if you can see the difference between being in the higher managerial and professional category and the lowest category, the least affluent category, long-term unemployed, it's 3.478 marks. So that's quite a substantial difference in what the model will predict a case will get, depending on which of those two social economic class categories they belong